to get through work and energy. You'll find that work and energy is much, like energy conservation, is much more mathematically friendly, right? There's no vectors. It's a lot more just, oh, here's what's happening here, here's what's happening here, set them equal to each other. A lot like we did in the last lab where we were shooting the pendulum. So it's just algebra. It's not as many vectors and not as much calculus. There's sort of a movement in physics to start this class with this topic, but it's nice to have a little break in the middle of the semester. So we'll get through energy and momentum conservation. They're kind of nice, and it's also, I think, the most important concept that we cover in this class because it really is the key to like all of how science works. Like energy conservation can be as simple as like you're trying to lose weight, you need calories in versus calories out, right? So energy has to be conserved, it has to go somewhere. And you can solve, whenever you're like thinking about a problem in physics or engineering, the best place to start is always with energy conservation, okay? If you don't get the information you need, you can go back to forces and kinematics and all that stuff, but it's always a good place to start. So just a review of where we've been since we've had a week off. We've lost a TV. Let's see. We have sort of essential topics and basic goals. We've talked about particle acceleration, we've talked about force, we've talked about interacting forces, okay? We want to know how does a particle, and when we say particle, we just mean any object, but we're not, sort of the difference between particle and like, the other term you would think of in physics is like rigid body, which means like something you can't approximate to a point, okay? So in physics, we always try to make things as simple as we can, and then we try to add complexity as we need it to get back to the information that we need. So anything that you can treat as just a dot, you treat it as a dot. If you can't treat it as a dot, then you start calling it like a shape, okay? And we try to keep our shapes simple. They end up being like spheres and cylinders and like cubes, like something that is easy to mathematically represent. And then you have to add more complexity as you go from there. So when we get into torque, we'll start talking about shapes and how their inertia changes based on the mass distribution of the shape. But right now we're still dealing with particles. So our general principles are, we have the Newton's laws, okay? With the caveat that sort of the fourth one is the gravitational formula. And then we find that Newton's first law, if I go backwards, is it gonna go all the way up? It's gonna go all the way back. The first law is like if your velocity is not changing, you don't have acceleration, you don't have a net force, okay? The second law is our force equals mass times acceleration. Don't forget these are vectors, so that includes breaking things into x, y, and z, or r, t, and z, or whatever coordinate system you're using. And then the third law is just that you have these action-reaction pairs. So if you have interacting objects, you want to find the paired forces that are the same so that you can solve your equation more easily. The basic problem-solving strategy is always to break things into the coordinates along your axes and then set up Newton's second law. There's some in circular motion, we have this extra layer of stuff. It's the same idea, but remember we have a slightly different coordinate system and we have slightly different ways of describing acceleration because we have centripetal acceleration, which involves velocity, okay? Kinematics is you don't have to memorize all this stuff, but if you want to look at it during like when you're making like a cheat sheet for a test or something, it's all there in the slides. We have these special uniform acceleration, uniform velocity for linear and trajectory kinematics, so anything moving in a line or following a parabolic trajectory. We have circular kinematics, so that includes knowing what period and frequency are, and also our angular coordinate systems, right? So alpha, omega, theta, how do you use those in kinematics? We can go back and forth. And then the real basics are, we know that acceleration is the derivative of velocity with respect to time. We know that velocity is the derivative of position with respect to time, okay? So this is like the most general you can get. Like if you really wanted to sort of start with the simplest amount of equations, you just kind of need these and these. And you could really come up with anything else on here from those things. The only thing that's tricky is like the circular motion. You might want to write down the period and frequency or inverses and how is that related to radius and circular things, okay? All right, so we're going to talk about work and kinetic energy. This is sort of how we transition from force into energy. And we're gonna have to just come up with some definitions to start out with. So we'll talk about work and the definition of work, then we'll talk about how work relates to kinetic energy, then we'll talk about different forces and how they give us different potential energies essentially. And we'll talk a little bit about power. That's really only a couple of slides, okay? So in order to talk about work, the first thing we have to do is describe what a system is. And that sounds really complex, but it's really, really not. So like for instance, this can be a system, right? So a system is just the objects you include in your problem, essentially. Okay, so a system is, a fancier way to say this if you want to impress your friends at parties is that a system is a small subset of the universe, but it's really like the system is this remote, okay? Examples, single object or object you can treat as a particle, right? A collection of objects and particles, so I could have a system that's like the remote and my orange juice. I think this is orange juice, it's unclear. And I could like involve the table too, or I could involve the entire room, right? It's where just like coordinate systems, a system has boundaries where you set them for the problem, but you just have to remember what you included in your system so you know if, basically when we talk about energy conservation, you need to know if the energy is entering or leaving the system, right? So if it's all contained in the system or if it's not, you write the equation differently depending on how you define your system, okay? It could be a region of space. This happens a lot more in thermodynamics. So you could be like, oh, there's this many particles in this box or just in this room, and then you heat them up and how fast are they going, that kind of thing. And then you can have a region which varies with time and size or shape. So let's say you have a cylinder with a piston, right? Your system could just be whatever's inside the cylinder, but if the piston moves, it changes volume, things like that. Okay, so when we get to thermodynamics, that comes up a lot more. But for our purposes, we're going to deal mostly with just objects, all right, for now. And a system boundary is just an imaginary surface. Yeah, that's fun. That divides the universe into the system. So like if this is my system, it's all of these things contained by those. And then the environment is like the table and the air around it and me touching it. That's the environment, okay? So really simple, but we're using this new terminology, okay? So let's just talk a little bit about work. So here's two situations and decide which one you are more comfortable with. So this guy owns a piano and like heavy objects, several pianos apparently, and he wants to move next door. And this guy needs to move to California, but he has a box of pillows, but you have to carry it, okay? So which one of these is a better situation? Well, think about the variables involved, right? What's bad about this situation? Yeah, it's the mass, right? You have this mass problem, right? There's not a lot of mass here, but there's a lot of mass here. What's wrong with this situation? Distance, right? This is a short distance with a large mass. This is a large distance with a small mass. And so remember, exerting force to move something over a long distance means you will be doing more work. So work includes both of these variables. And so you would say, well, these are about the same amount of, well, they're like equivalently large amounts of work. Okay, this is a small amount of mass but a large amount of distance. This is a large amount of mass but a small amount of distance, but both of those things are included in work. So those are both a lot of work and you should probably just get new friends. So yeah, there's a definition of work and we're gonna go through like a more formal definition, but just for our purposes to get started, work is approximately equal to force times distance, okay? So it's actually an integral, but just start in your brain that work is force times distance. And there's a couple more things that are at play here. There's an integral and a dot product, okay, that we're going to deal with because direction is going to matter. But let's start with talking about the sign of work. So work is positive, and remember this distance is a displacement. So remember displacement is a vector, which means it has a direction, okay? So for instance, if I walk from here to here, which way does my displacement point? This way, this way, this way, okay? If I pick the staples up from here to here, which way is the displacement? Okay, so the delta R can be treated as a vector and the displacement matters. So work is positive if the force and the displacement are pointing in the same direction, and it's negative if they're pointing in opposite directions, okay? So just as an example, we're not worried about time or anything yet, just displacement and work. So if, let's say this guy, Sisyphus? Anyone know their Greek mythology? It's the guy that pushed the rock up a hill all the time. Okay, well, it's not a Greek class, that's fine. This is force, almost all my Greek mythology comes from reading Percy Jackson, so it's like pretty, at least recently. I think I read an actual Greek mythology textbook at some point, but I've been reading Percy Jackson with my son, and it's fun, but yeah, my Greek mythology is very spotty. So, force up, displacement up. So if this guy's pushing the rock and it goes up the hill, is the work positive or negative?
Negative. Oh, wait, no.
Positive, okay? So this is positive, he's happy, he's exerted force, he got the rock to move in the direction he wanted, he's happy, okay? In this situation, this guy is pushing this rock with the same force, but it's not moving, okay? What's the work here?
Negative. Oh, wait, 0. Oh.
Zero,
Yeah,
right? So the displacement's 0, that means the force doesn't matter, right? The work done is 0, okay, which kind of sucks. So he's not stoked about this, okay? Now, this guy's pushing with the same force, but the rock is rolling down the hill while he's trying to push it up. So they're both sliding down the hill. What work is this?
Negative.
Negative. And so in this case we would say, and he's sad about it, in this case we would say the rock is doing work on him. Okay, so here he's doing work on the rock, here there's no work being done, here the rock is doing work on him. Okay? Alright. So if another example, so if I'm holding this thing up, so let's say I lift it from here to here, what work, so what would you call the work I'm doing? Is that positive or negative?
Positive.
Positive. The force from my hands is pushing up, right? The displacement is up. What about the work done by gravity? Negative, right? So the displacement is in this direction, the gravitational force, the weight, is in this direction, so the work done by gravity is negative. So I'm doing work against gravity. Okay, this is, so depending on which, so remember when we talk about force diagrams, we've always talked about net force. Now we want to talk about the work done by individual forces, okay? We still care about net force, but we always want to know, okay, which force versus which displacement gives us the work, okay? So in this system, if the system is staples in a box, I do work on the staples to get them, in this case, a higher potential energy. Okay, and then the gravity does work against me. Okay, all right. So gravity's doing negative work. So we're gonna try an example. Let's say we lift a crate of mass 5 kilograms from the ground to a height of 1.3 meters at a constant speed. Okay, why do you think we need a constant speed? What do we not have then? Acceleration, yeah. So just to make things simple, this constant speed means we don't have acceleration. Okay. So we'll draw the picture. So here's our ground. And we've lifted the crate up here at a constant speed. This is a height. So we have a displacement of delta y, which is equal to 1.3 meters, 1.30 meters. What are our forces? Gravity, right? So weight, that's going to be mg. Anything else?
Force of lift.
Yeah, the lifting force, right? Let's call that lift. And because we don't have acceleration, right, we explicitly said acceleration is 0, what do we know about these forces?
They equal each other.
Yeah, they should be equal and opposite, right? So they should be the same. So that means we know that if we sum up our forces in the y direction, we know that F lift minus mg equals 0 because acceleration is 0. So that means F lift is equal to mg, okay? So we want to know how much work we did. And for now, our definition of work is just force times delta R in this case. In this case, it would be delta Y, okay? Which force is our force? F lift. So we can rewrite this as F lift delta Y. Okay, do we know what F lift is? Can we calculate that? Yeah, we have a mass, so we know this is 5 kilograms times 9.8 meters per second squared. So that should give us 49 newtons. Okay, we could even round that to 50 if we're feeling lazy. And then how do we figure out work? Well, we just calculate it by multiplying that force, 49 newtons by 1.30 meters. And that means we have a lift, work done by our lift of 63.7 newtons times meters is joules, okay? So just as a side note, a joule, if you break it down, is kilograms meters squared over seconds squared, but remember kilograms meters per second squared is a newton, so newtons times meters gives you joules, and that's just our units. Okay, is this positive or negative? 63.7 joules.
Positive.
Positive, because our force points up and our displacement points up, okay? Then we want to figure out the work done by gravity. Is it going to be any different from the work done by the lift? Well, what'll be the main difference? The sign, right? So we'll have mg as our, sorry, it needs to be work. So the work of gravity, this is the work of the lift, is going to be mg times also delta y. In this case, we still have 49 newtons times 1.30 meters, but this is going to give us a negative 63.7 joules because we know gravity points down while displacement points up, okay? So that's how we use work in our problems. This is the simplest possible situation. We don't have any acceleration, we don't have any changing forces, so it's just displacement times force, okay? All right. So in this case, just as a side note, what is the system? What did we think of as the system?
The crate.
The crate. And what's the net work on the system?
0.
0, because if you add up, there's two ways to do this, right? If the net force on the system is 0, the net work is the net force times the displacement, but 0 times anything is 0. If you want to do it the other way, you could calculate the work done by gravity and the work done by you, right, which point in different directions, and then you have 63.7 minus 63.7, it's also 0. So the net work is 0, but that doesn't mean that there's not work being done, okay? And that's because we've chosen the crate as our, so what other things could we put into our system in this case if we really wanted to add things to it? You can put the ground in the system. You can put your hands into the system, right? So then that work would be internal work, right? There would be that force would happen inside the system instead of being an external force that happens to the crate. Okay, so that's where the boundaries start to matter, is when you're deciding if it's work coming from outside your system or work coming from inside your system. Okay, the way if we set up the system as the crate, all the work done is done by outside forces. If you include yourself in the system, then the lifting force is internal to the system. Okay, and this will come up more specifically when we get to more complicated problems. That problem's pretty simple. So here's a physics riddle. Why is kinetic friction so sad? That is one of the answers. All right, well, it only does negative work. Now remember, how is friction as a force defined compared to movement? Always points in the opposite direction. So if I'm sliding this stuff this way, right? The friction has to be that way. So the friction force always points opposite to the displacement and therefore always provides negative work, okay? And here's the secondary thing. It's sometimes a drag, okay? This is what you're here for, I'm sure, these puns. All right, so just before we get into the next part, just a little bit of review. We talked about this in the very first week of class, but it's probably fuzzy. So remember, the scalar product of two vectors, also known as the dot product, looks something like this, okay? And what does it tell you about the two vectors? What does it really represent? What's the ideal configuration of two vectors if you want to maximize your dot product?
Magnitude?
Yeah, if you want the biggest magnitude, should the vectors be pointing the same direction, different directions, perpendicular? What does it?
Same direction.
Yes, a dot product really gives you the parallelness of two vectors, okay? And so when we're talking about work, we've noticed positive means pointing in the same direction. Okay, negative means pointing in the opposite direction. What do you think the work is if you're perpendicular?
Like 45.
Well, 90 degrees, yeah.
Perpendicular.
Yeah, so if your displacement and your force are perpendicular to each other.
The work direction's 90 degrees.
So 0 degrees, 90 degrees, 180 degrees. 0 degrees means maximum. 180 is minimum because it's a negative value. What's 90 degrees?
0.
0. And that's what a dot product tells us, right? The cosine of 90, cosine of pi over 2 is 0, okay? So if we have two vectors and they have an angle between them, the dot product it gives us either the projection of B on A, meaning like the component of B parallel to A, or the same thing, projection of A on B, so the component of A parallel to B. So you really want the vectors to be parallel to maximize the amount of work. If they're anti-parallel, that gives you a negative value. And so that's where the sign comes from. That's why we're saying if work and displacement are in the same direction, it's positive. If they're in the opposite direction, it's negative. But it's actually more complicated than that because if the vectors are at an angle to each other, you can get some smaller fraction or 0, okay? So we're sort of getting to work, and this is not the full definition, but it's the full definition if it's a constant force, okay? And we'll get to what we mean by that in a second, but we're adding more complexity to this. So in this case, work is actually the dot product of force and displacement, okay? So for a constant force, work is the dot product, meaning that the sign comes naturally from the math. Now we don't have to say, okay, if they're parallel, then it's positive, right? So for instance, if we have a force in this direction, right, you don't use the full force. It would be FR cosine theta, so this angle here, okay? Or it's the component of the force that's parallel to the displacement, and then you just multiply them together, okay? So remember, they have to be parallel for the force to count. So here's our definition, and that's going to mean that the box, if you put all this force in this direction, right, if you redirected it, you get more work. But because the force and the displacement aren't parallel, you're going to get less work, okay? So work is a scalar product, meaning if things are parallel, that's your maximum and work is positive. So the angle between these two vectors is 0. You get, this is what we've been talking about so far. Okay, if they're anti-parallel, this is how you get your negative value. And then if they're perpendicular, you're gonna have a work of 0. Okay, so here's our second physics riddle of the day. Why are centripetal forces so lazy? So I want you to think about the force versus the displacement. Which way does the centripetal force point?
Towards the center.
Towards the center of a circle. Which way is the displacement? Around the circle. Are those are perpendicular because that's tangential. So you have a tangential displacement, a radial force.
Doesn't exist.
They never do any work. Okay, that's why they're so lazy.
Thank you.
Thank you for that. Okay, I'll be here all week. What that means is every time you have centripetal forces, they don't do work. Okay, so just as a thing to remember. So let's try our first clicker questions. Oh, just as a side note, right? So let's say I have these again, but instead of bringing them up and down like this, right? This obviously does work, okay, because the force of gravity and therefore my lifting force are in the y direction. What if I just like move this way? How much work did I do on this box? None, right? Because all of the forces are in this way, in this plane, but I've moved it laterally, right? So if I move it in x, but the forces are in y, there's no work done, okay? At least not from gravity. Okay. So here's our first question. Mostly thinking C, but we got some A's and D's. The chat is mostly C, so please discuss. We'll vote again.
C.
C, perfect. Yes, the answer is C. But if we want to go through these, right? What's the work done here?
0.
0. What's the work done here? It's like R times 8 times, what's 8 cosine 60? Anybody? 4, right? Cosine 60 is 1/2, so this is going to be 4 times R. So this would be 0, this is 4 times R, and then this is 6 times R because they're parallel, okay? So that's cosine of 0. That means the 6 Newton force is doing the most work, all right? Cool, now you're good at dot products, yes?
So for the first one, the one that's perpendicular, does it matter how far like the distance you travel is, like as long as it's parallel, it's 0?
As long as it's perpendicular, it's 0, yeah. So yeah, the size of the force, the size of the displacement, doesn't matter. If the angle gives you 0, the whole thing is 0, yeah. Okay.